Hey y'all, if you are here, I'm assuming you've already read the problem, so if you haven't already, just take a look at it, and I'm just going to explain it in an easier way. So we're given a 2D matrix, an m by n, and we are just asked to rotate it. So we're looking at this example right now. We're either given a falling stone, an empty space, or a stationary object. So these stationary objects, these two asterisks right here, these are going to be rotated clockwise to over here. Same with the rest of the objects that we're looking at. So these falling stones will actually begin to fall. So this object right here is going to fall from here to here. And that's pretty much the problem. We want to take some 2D matrix, rotate it 90 degrees, and after all of the falling stones have fallen, what is our 2D matrix going to look like? And we want to return this new 2D matrix. So how do we approach this problem? Let's break it down into steps. What exactly do we need to do first? First, we need to try and figure out how to rotate this, how to get these static objects into this next portion. And then from there, afterwards, we can try to figure out how to translate these falling stones. So here we have a 5x4 matrix, and let's just write down some stones that we're going to be turning. So we have 0, 1. Let's do also this 2, 1. Let's also do this 4, 1. And let's actually do a rotation. And let's actually rewrite these now. So we have 0, 1, 2, 3, 0, 1, 2, 3, 4. And let's see what this actually looks like now. So at this same static object, we can say this is going to be 1, 3. This one is going to be 2, 2. And this one is going to be 4, 2. Now, if you want to try and give this a shot yourself and figure out what actually is the relation between these two, go ahead and pause the video. But I'm going to tell you right now, assuming that you've unpaused it, that to get from these green numbers from our original to these orange numbers, our new, the conversion is going to be, so let's just say this is x, y. Our new x value is just going to be our y value, and our new y value is actually going to be the complement of our x value. So that's just going to look like the length of our current x value, or whatever our length is, minus 1 minus x. So let's set up our solution. And it's just going to look like this. I assume you already know what all of this is, so I'm just going to leave it as it is. And we're going to iterate over all the elements in our boxes. And we're just going to use that equation that we found in our picture example to set up our graph. And let's do a quick sanity check to see if this is coming out correctly. So we can see that our original is converting to our new answer. Yeah, this is looking good. Let's check our third example. This is going to be over here. This is going to be in the middle. Yeah, so this is looking fine so far. Now that we got our rotation down, let's start to work on having these falling stones translate to the right position. So what I'm thinking is we're just going to look at our translated graph, and we're going to say, moving from bottom to top, if we find any falling stones, we're just going to take the accumulated counted stones, and from our last either static objects, so one of these guys, or our ground, we're just going to count up from the bottom those stones that we saw until our either top of the graph or our next stone, or our next static stone. So what I mean by that was we're going to count from the bottom up, and we're going to say, whenever we see a static stone, we're just going to count all of the falling stones before it, and we're going to repeat our count from our last static stone and just add all falling stones from the bottom up. So in this case, we're just going to say, counting up from here, we see 0, 0, we see 1, we see 2. So now that we see a static stone, and we have 2 falling stones that we've seen, we're going to count from the last static stone, or the ground, up until that static stone again. And we're just going to say, all right, we saw a falling stone, so we're going to put a falling stone here. We saw a falling stone, just put a falling stone here. And that was our 2 that we've seen. So now the rest of these are just going to be empty spaces now. And then we continue again. So from our static stone, this is going to be our new ground. We see 1 falling stone. Cool. We see only 1. We see only 1. We hit the top and we say, all right, from our last static stone, put a falling stone down. We have 0 left. So we're just going to put nothing, nothing. From this side, we're just going to do the same thing. We see 1 falling stone, 1, 1, 1. So after we hit our static stone, put down the falling stone, put down nothing. Start from here. Do we see anything? No, we don't. So we're just going to put down nothing because we hit this static stone. And we're just going to keep going up again. So from the static stone, from this static stone up, we see 0, we see 1, we see only 1 so far. We hit our top. And then from our last static stone, we're just going to put down our falling stone, nothing, and then nothing. So in our picture example, we were using this new rotated graph for our answer. But instead, it's actually going to be easier to program in this if we continue to use this one. And then whatever we find, we're just going to translate it to here. And we could start with this. So this would be iterating from the rightmost to the left. It actually doesn't really matter. We could just start with either this, or what I'm going to do instead is just do this. This is a portion, however, that's non-negotiable. We have to iterate from the bottom up, or if we're working with our pre-rotated matrix, we need to start from the right to the left. So from our first element to our last element, again, this is exclusive. And then this just means that we're decrementing instead. So we're going from a high number to a low number. So let's get our stone count. Let's get our current ground. This is going to change whenever we see a static stone, but for right now, it's just going to be our last element. So our last element, or actually rather beyond our last element, because we're not going to be including this element. Whenever we see a falling stone, we're just going to increment our stone count by 1. And whenever we see a static stone, we need to figure out some fall function. We're going to update our ground, and we're going to reset our stone count because, again, we're going to fall. And after that, we don't want to interfere with any other stone count after we find our new quote-unquote ground, this. So what are we going to need for our fall function? Well, clearly we're going to need our x and y values. So let's pass this I and j. And we're also going to need the stone count as well. So stone count, and then let's pass in our ground as well. So let's create this function, def fall. Let's pass these in here, but also let's just call this x and y. And I want to rename these just because I know that I'm going to be using I and j in the future because we are going to be doing some sort of iteration within here. So what is that iteration going to be? For what? We know that we're moving from right to left. Again, we're not using this rotated graph. We're going to be moving from right to left. So we're going to say something along the lines of for j in range what? We're going to be starting from our last ground. So either the end of this or wherever we see a static stone. For range, we're going to be starting from ground, and we're going to be going to our what? To our current y value. And why is that? Because whenever we find a falling stone, we pass in this I and this j, and we just want to return back to our last column. Because that's the only time we're ever going to stop. The only time we're ever going to stop is when we see a static stone or we see the end of the graph. So from our ground to this y value, -1. Because we're going from a higher number to a lower number. And also, we just want to do ground -1 because we don't actually want to include the ground itself. This is going to be exclusive, and now we've just made our ground exclusive as well. So moving from right to left, if our stone count is greater than 0, we're going to make our x value our y value, and we're going to make our y value our complement of our x. Again, this is something that we've seen before. And we're just going to put our falling stone here. Then we're going to remove a stone from our stone count. And if we have gone beyond removing all of our stones, all other spaces that we see are just going to be empty spaces. All right, cool. So this should take care of our falling function. Now, up until this point, we've only been using this for whenever we see a static stone. But once we finish up observing all the elements in our row, we just want to make sure that we're going to be calling this again. So fall. And then for our y value, we just want to pass -1. Because again, whenever we pass this value, it's always going to be exclusive in this function. So we just want to put our most left value. Then we're just going to pass the rest of this function, which is just stone count and ground, which don't change. All right, cool. Let's return our answer. Return answer. Run it. Looks like it's accepted. Submit. And then there we go. A link to the code will be in the description. Like, subscribe, join our Discord for extra help, problem suggestions and announcements, and I'll see you in the next one.